Drilling fluids, often called drilling mud, are essential in creating boreholes for resources like oil, gas, or geothermal energy. This fluid is a carefully engineered mixture performing many critical functions. It circulates down the drill string and back to the surface, vital for successful well construction. The primary purpose of drilling fluid is to aid the drilling process by cooling and lubricating the drill bit, reducing friction and wear. It carries rock cuttings to the surface, keeping the borehole clean and preventing the drill string from getting stuck. Another critical role is maintaining hydrostatic pressure to control subsurface pressures and prevent blowouts. The fluid also helps stabilize the uncased sections of the borehole, preventing collapse. There are several main types of drilling fluids: water-based muds, WBMs, oil-based muds, OBMs, and synthetic-based muds, SBMs. WBMs use fresh or salt water, are less expensive, and more environmentally friendly. OBMs use diesel, mineral oil, or synthetic oils, offering excellent lubrication but posing greater environmental concerns if spilled. SBMs are designed to have the performance of OBMs but with lower toxicity. Each type is chosen based on specific geological conditions and environmental regulations. Drilling fluids contain various chemical additives to fine-tune their properties. Barite increases fluid density to control formation pressures. Bentonite clay increases viscosity and builds a filter cake on the borehole wall. Polymers control fluid loss and improve cuttings transport. Corrosion inhibitors protect the drill pipe and casing from chemical attack. Biocides prevent bacterial growth that can degrade the fluid. Other additives might include shale inhibitors, defoamers, and pH control agents. The exact mix varies greatly based on the drilling conditions and requirements. Once pumped into the well, drilling fluids interact directly with geological formations. As the fluid circulates, some liquid filters into permeable rocks, leaving solid particles behind to form a filter cake. This filter cake seals the borehole wall, reducing fluid loss and stabilizing the well bore. However, if not managed correctly, it can damage the permeability of oil or gas-bearing formations, reducing well productivity. The chemical nature of the fluid dictates its reaction with different rock types. Chemicals within drilling fluids can alter the local underground environment. Highly alkaline fluids can react with certain minerals, changing the rock's strength or fluid holding ability. Some chemicals might precipitate out due to temperature or pressure changes, potentially clogging rock pores. This could affect groundwater flow if the drilling fluid enters an aquifer. The extent of these interactions depends on the fluid's composition, rock type, and underground conditions. Careful fluid design aims to minimize unwanted interactions. Potential pathways for drilling fluid chemicals to reach aquifers include well integrity failure and geological factors. The wellbore is lined with steel casing, cemented to isolate it from surrounding rock and groundwater. If the casing corrodes or the cement job is poor, leaks can occur, allowing fluids to escape and migrate into nearby freshwater aquifers. This is a risk in older wells or areas with less stringent construction standards. Maintaining well integrity throughout the well's life is crucial. Natural fractures or faults in rock formations can act as conduits for chemicals to travel. Highly permeable rock layers intersected by the well can also allow fluid migration if not properly isolated. Surface spills during mixing or handling are another concern. If not contained quickly, these spills can seep into the ground and potentially reach shallow aquifers through soil infiltration. Proper site management and understanding local geology are vital to prevent this. The environmental impact of drilling fluid chemicals on aquifers is a significant concern. Some additives used in drilling fluids can be toxic. Heavy metals and hydrocarbons are pollutants. Even small concentrations can render water unsafe. Current practices focus on managing drilling fluids to minimize harm. Used fluids and cuttings are collected and treated. Treatment methods include separating solids from liquids. Disposal methods include deep injection or landfill burial. Strict regulations govern handling and disposal. Mitigation strategies protect aquifers from contamination. Designing less toxic drilling fluids is key. Improving well construction prevents leaks. Continuous monitoring detects early signs of contamination. Strong regulatory oversight is essential. Combined measures reduce risks to groundwater resources. If you find these videos interesting, please like and subscribe. Thank you.